I'd like to talk a little bit about graphing polynomials. And the first thing that we looked at, zeros, was really important for graphing polynomials. The second thing is called multiplicity. So with multiplicity, I think we talked about what that actually looks like in an equation, but I'd like to talk about what it means for the graph. So first of all, I wrote out that the sign of your f of x does not change from one side of the zero with the even multiplicity to the other. The other thing that's really important when you're graphing it is that the graph is going to touch the x-axis and bounce back. So I'll give you an example and you can see what it looks like. Let's say we have y equals x minus 2 squared. That graph, you might be able to remember that we are going to have our, it's pretty much the y equals x squared except shifted 2 to the right. So that one looks like this. So my 0 is at 2, and I want you to notice that as the graph is going down, it goes towards 2, and then when it hits 2, it bounces back. So I like to say that my graph has a bounce in it. And if you have any other even exponents like this, you're going to have a similar idea. You're welcome to try on your own graph y equals x minus 2 to the 4th to the 6th. What you'll notice is that the graph might become a little bit wider, but it has the same behavior. It will still bounce back at x equals 2. So for an odd multiplicity 0, you're actually going to have the graph crossing through that 0, and the sign of your function changes from one side of that 0, r, to the other. So there's a special case. If your multiplicity is bigger than 1, like if it's 3, 5, 7, 9, and so on, your graph's going to have a little squiggle in it. I don't really know, I don't think there's a technical term for that. Bounce is also not really a technical term, but let's do an example. I'll show you what I mean. So let's say we have, let's start with one where you have a multiplicity of 1. Let's say that you have y equals x plus 3 or something like that. That one has a 0 at x equals negative 3. And there's a y-intercept at 3 also. So that looks like this. You can see we have a multiplicity of 1, and the sign of the graph changes from one side of that negative 3, that 0 at negative 3 to the other. It just kind of passes through. Now let's say you have something like, this is my second example, if you have something like y equals x plus 2 to the 3rd power. So if we graph that, you might remember that the graph of a cubic function kind of looks like, it's like two half parabolas, like one on top of the other, but they go in different directions. So that one looks like this. And you'll notice that we do go through at kind of a little squiggle there. It's a weird, it changes from being what we call concave down to concave up. You don't need to know that right now. We're going to learn about that in calculus next year. The big thing you just need to know for this is that we get this kind of behavior when we have an odd multiplicity that's bigger than 1. So go ahead, pause the video and try this problem. So our zeros are going to be at x equals 0. That one has a multiplicity of 1. Then we also have x equals negative 1, which has a multiplicity of 2. And then we have x equals 3, which has a multiplicity of 3. So at x equals 0, that one is just going to pass through. At x equals negative 1, that's going to bounce. And at x equals 3, that's where we have our squiggle. So let's go ahead and draw this. It's not going to be completely drawn to scale, but hopefully you'll get the idea of what it looks like. So we know that we have zeros at 0, -1, and 3. I'm not going to worry about my y values yet. I just want you to get the basic shape of it. So we know that when we come to -1, we have a multiplicity of 2, so it's going to bounce back, and then it goes back up. I'll explain how I know that it's above the x-axis and not below later on, in just a few minutes, in fact. So now I know that I'm going to go back down through 0, 0, and I'm just going to pass through. I'm not going to bounce back. I'm not going to have any sort of weird squiggle, so just go straight through there. Then, when I get to x equals 3, that's where I have that little weird squiggly thingy. So it should look kind of like this in the end. My end behavior, my end isn't perfect, so I'll fix it and make it look a little bit better. It does keep going out to the right, so it ends up looking like that. So just a few other little things, and then we're going to do one big thing. So the first thing is, if f is a polynomial of degree n, then it has at most n minus 1 turning points. So if that doesn't completely make sense, I'll give you an example. So for example, we have f of x equals x minus 1 squared times x plus 3. So even if you have no idea what that graph looks like, we do actually have some idea because we just talked about multiplicity and zeros. We can figure out, based on our degree, how many times it's going to turn around. So our degree here is 3. You can just add the exponents of your factors. So that means that it has at most 2 turning points. So actually this graph is going to look like this. You can see that it does have 2 turning points there. The converse is also true, meaning like the opposite direction. So if we have n minus 1 turning points, the degree has to be at least n. I'll give you a quick example of that. So if you get something like this, it's super complicated. I don't actually know the equation of this without more information. But what we can do is we can figure out the lowest possible degree. So if you look at the number of turning points, there are these things right here. Those are my turning points. You'll notice I have 5 of them. So that means that my function has a degree of 6 or more. So the last thing I'd like to talk about before we actually can start graphing is the end behavior of a function. So the end behavior of a function is the behavior of the ends of the graph as your x values get bigger and bigger and bigger, or we say approaches positive infinity, or gets smaller and smaller and smaller, or we say approaches negative infinity. So keep in mind this is your x. So right here is where x is approaching positive infinity. That means x is getting really, 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 really big. And in this case, this is an example, by the way. I didn't write that, but you have a lot of different graphs where you look at end behavior. And in this case, as x approaches positive infinity, your y value is getting really, really, really negative. So we say that that our y is approaching negative infinity. Now, if we look in the other direction, we can see right here that our graph is, as our x values are getting more and more negative, which means we say that x is approaching negative infinity. As that happens, our y values are getting really, really big. So we say that y is approaching positive infinity. So the way that you can kind of figure out, based on an equation, how the end behavior of the graph is going to be is based on the degree, whether it's even or odd, and based on the leading coefficient, whether it's positive or negative. So I'll give you a table where you probably just want to copy down or take a picture of, that you can reference as you're doing these practice problems. So we're going to have 4 situations, depending on if the degree of your polynomial is odd or even, and depending on if the leading coefficient is positive or negative. So if your degree is odd and the leading coefficient is positive, you are going to have the following end behaviors. So you're going to find that as x approaches infinity, y is going to approach infinity, and as x approaches negative infinity, y is going to approach negative infinity. So I'll show you an example. This is one that you actually know. One example is y equals x to the third. Your leading coefficient of that is 1. Your degree is odd. So if you were to draw that graph, as our x values got bigger and bigger, our y values would get bigger and bigger. As our x values get more and more negative, the y values also get more and more negative. And you might be able to guess what the other ones look like based on the graphs of like y equals x squared, y equals negative x squared. If you want, you're welcome to try to fill in the rest of this on your own, or you can just watch me do it. So if the degree is odd and your leading coefficient is negative, for example, if you have like y equals negative, we'll just say negative x, that has an odd degree. It has a degree of 1, and it has a negative leading coefficient of negative 1. So for that case, as x approaches infinity, y is going to go towards negative infinity, and as x approaches negative infinity, y will approach positive infinity. So this example I gave you here is going to, so as x approaches infinity, y approaches negative infinity. That's going to look like this part. And as x approaches negative infinity, y approaches infinity. That looks like that. So then let's do the other two. If you kind of figured out and are able to guess what it looks like, again, you can try it on your own. So, by the way, this example here is not part of the table, so just be careful about that. So if your degree is even and your leading coefficient is positive, an example of that is if you have like y equals 2x squared or something like that. The leading coefficient is positive 2, degree is 2. So for that type of equation, you're going to actually have all y values, all end behaviors for the y's going towards positive infinity. And part of that is because our range is y values that are always positive. So the first part I said, as x approaches infinity, y approaches infinity. That looks like that. And the second part is as x approaches negative infinity, y approaches infinity. That looks like this. So then our last one, I'm just going to do y equals negative x squared. I think that you guys recognize that one probably better than any other that I might give you. So for this one, it's going to be the exact opposite for the y values as the one above. So our y values as x approaches positive infinity are going to go towards negative infinity. And as x approaches negative infinity, they're going to go towards positive infinity. So let's draw that on the graph. So we are going to have a graph. So the first part, as x approaches infinity, y goes towards negative infinity. That looks like that. The second part, as x approaches negative infinity, y approaches, this should also have a negative there. I lost that. It should look like this. So even if you don't quite understand these yet, just make sure you have them in your notes. We'll do a bunch of examples of these in class tomorrow.